Good morning and welcome to this fourth module of Theory of Machines. Before we go into this fourth module, let us briefly review what we have covered in the previous modules. In the previous module, we defined what is a kinematic pair, we defined what is degree of freedom, and then examined several kinematic pairs. In particular, we have studied the relative motion occurring in a revolute pair, a sliding pair, a plane pair, a spherical pair, and a screw pair through animations. Having said that, let us see what are the learning outcomes of the current module. By the end of this module, you will be able to explain the classification scheme of kinematic pairs. You will be able to specify the degree of freedom of a kinematic pair and also specify whether it's a lower pair or a higher pair. And you will be able to specify whether it's a form closed pair or a force closed pair. With that learning outcome set, let us briefly see what we have for this current module. The current module will see that classification scheme of a kinematic pair can be done depending on the degree of freedom of the pair, depending on the type of contact occurring in the pair, and then depending upon the type of closure. We'll try to see each one of these classification aspects with the help of several animations in subsequent slides. So let us begin with the classification scheme depending on the degree of freedom. Before we do that, let us briefly try to recall what we mean by degree of freedom. Degree of freedom of a kinematic pair is the number of independent ways in which relative motion can occur in that kinematic pair. Okay. With that, let us see how we classify the kinematic pairs depending on degree of freedom. Okay. Very often this degree of freedom we'll abbreviate as DOF. Okay. Depending on DOF, you can classify a kinematic pair as DOF1, DOF2, DOF3, DOF4 or DOF5. Maybe all these examples are very much familiar to you. Many of them you have seen in earlier modules. However, I'll go over each one of them for continuity. The first pair here shown is a DOF1 kinematic pair. Okay. The only way in which relative motion can occur is rotation. If you fix this link, all that the other link can do is rotate about an axis. That is why sometimes it is called turning pair or revolute pair. Its degree of freedom is 1. Similarly, in this kinematic pair, all that this green link can do is it can slide in that hole. So it is called a sliding pair. Its degree of freedom 1. Similarly, this is a screw pair. Okay, nut and bolt. Though this nut can both rotate and translate, this movement of rotation and movement of translation, they are related by the pitch of the screw. Thus they are not independent. Because they are not independent, we'll say its degree of freedom is 1. So all these three pairs, they fall under the category of degree of freedom 1. Similarly here, what you see here, the kinematic pair formed by a brown link and a green link. You can see that this brown link can translate, it can slide, and also it can rotate. So its degree of freedom is 2. Similarly here, it's a spherical pair. I'm kind of trying to rotate and kind of trying to show how it is formed. Okay, you have a blue link and you have a green link. Okay, but once assembled, this green link has 3 rotary degrees of freedom. Okay. Similarly, in the case of this plane pair, this blue block can have translatory motion along x-axis, translatory motion along y-axis, and rotary motion about an axis perpendicular to the plane. So you have a degree of freedom 1 kinematic pair, DOF1 kinematic pair, DOF1 kinematic pair, a turning pair, a sliding pair, a screw pair, a cylindrical pair, a spherical pair, and this is a 3 degree of freedom plane pair. We'll try to see one example each of this dy of 4 kinematic pair and dy of 5 kinematic pair. Okay, what you see here is a kinematic pair formed by a cylinder and a plane. We'll quickly go over the 4 relative motions. We have one rotation we have already seen, translation along x-axis, translation along y-axis, and then rotation about y-axis. 4 degrees of freedom. So this is a dy of 4 kinematic pair. Similarly, the sphere plane kinematic pair is a 5 degrees of freedom kinematic pair. I would encourage you to go back and watch each one of these small animations once again and identify what are all the independent degrees of freedom. Okay, so to summarize this classification scheme, we say that degree of freedom will be in the range from 1 to 5. The next classification scheme is based on the type of contact. Okay, briefly, under this classification, kinematic pairs are classified either as lower pairs or as higher pairs. In lower pairs, surface contact occurs. Okay, when surface contact is occurring, there is lot of area for taking the load, and thus the contact stress, which is the normal force divided by the area of contact, is small, is lower. That is why it is called lower pair. Okay, if you quickly look at this animation, the green link and you have a brown link. Okay, see what kind of contact is occurring. Contact occurring here is along a cylindrical surface. Okay, because it's cylindrical surface, you have lot of surface to take the load. So stress, which is load divided by area, is lower. That is why it is called a lower pair. The same is the case here. In the case of this spherical pair, when once the sphere comes and stays in here, see what kind of contact is occurring. The contact is along a spherical surface. Because the contact area is more, the stress is lower. So you call it a lower pair. As opposed to this, in these two kinds of kinematic pairs, you have either line contact or point contact. In either case, the area available for taking loads is much smaller. So the contact stresses are higher. Consequently, this pair is called a higher pair. Let me try to animate this. Okay, you can see in each case that all through the duration of relative motion, there is either a line contact or a point contact. So the stresses are higher and we call it a higher pair. Okay, so based on type of contact, you can classify the kinematic pairs as lower pairs and higher pairs. This is another classification scheme wherein you see how contact is maintained. If the contact is maintained because of geometric form, you call it a form closed pair. Whereas if the contact is maintained because of force, some kind of external force, we call it force closed pair. Let us try to take a look at it. Okay, this is a familiar example. We have seen it a couple of times earlier. Once the green link is placed inside, the cap is closed and somehow tied together so that the brown elements form one kinematic link. Once this is done, the green link cannot do anything. It is trapped inside. All it can do is rotate. So while the relative motion is occurring, the contact is maintained only because of geometric form. So this revolute pair shown here is a form closed pair. Similarly, in this case also, you don't have to apply any force to maintain contact. Contact is always maintained because of the geometric form. Similarly, in this case, once these two blue halves are assembled in place with the green link inside, This blue halves form one link, the green part forms one link. Once these are assembled, the green link is trapped inside. It cannot do anything. So to maintain contact, you don't need additional force. So these three stand as examples for form closed kinematic pairs. As opposed to this, you have these two situations in which you need to have a spring here, a spring loading here to maintain contact between the cam and follower. I'll try to zoom in and show the kinematic pair as best as I can. Similarly, in the case of this sphere plane pair, the weight of the sphere itself is maintaining contact. Let me try to zoom in a little bit. You have this kind of blue link, which is the cam. The green one is the knife-edged follower. Okay, when the cam is moving, the follower needs to press onto the cam. That force of pressing is given by the spring. So this is a spring-loaded cam and follower. In any case, because an external force through a spring is needed, we call it a force-closed kinematic pair. Similarly, in the case of this sphere plane kinematic pair, the weight of the sphere is maintaining the contact. So we call it force-closed contact pair. So depending on the type of closure, you can classify the kinematic pairs as either form-closed or force-closed. Okay, so to summarize all we have seen so far, kinematic pairs can be classified into three different schemes. One, depending on the degree of freedom, you can classify it as DOF 1, 2, 3, 4 or 5 kinematic pair. Depending on the type of contact, you can classify it as lower pair where surface contact exists, or higher pair where line or point contact exists. Okay. Similarly, on the type of closure, you have either form closed or force closed kinematic pairs. So to summarize, kinematic pairs can be classified based on DOF, based on type of contact, based on type of closures. In lower pairs, we have surface contact and hence the stresses are lower. In higher pairs, we have line or point contact and hence the stresses are higher. Before we close this session, a little exercise for you. Wherever we see movement, we can perceive that relative motion is occurring and that there is a kinematic pair involved. Okay? Look around you and identify at least 6 instances of kinematic pairs. Okay? And try to classify them based on what we discussed just now. Thank you very much for staying with us. If you have any questions, comments or suggestions, please do email them to theoryofmachinesselftaught@gmail.com. Thanks. Have a good day.